Good morning and good day, everyone. Thank you for joining us. My name is Tony. I am a course advisor at EIT, and I will be your host to this session. Before we begin, I'd like to cover some few notes so that everyone get the most of out of the session. So on your screen now, these are the notification and sound options. You can turn on and off the notification and sound as you wish during this session. So please do post any questions under the Q&A function at the top right-hand corner. So if the questions are related to EIT's general offerings, programs, I will be able to assist regarding that. But if they are more technical and related to today's topic, our presenter for the day will be able to assist that at the end of the session. These are some of the frequently asked questions. So everyone registered for this webinar will receive a copy of the PDF slide and a link to the video recording within the next 2 business days via an email. So please do check your junk folder, spam folder, if the email does not appear in your inbox. We also provide you a digital certificate of attendance for live attendees. So there will be a QR code and a link shared to you after this session. So just stay with us until the end of the session to qualify for the certificate of attendance. Just a bit about EIT and ECT. So both institutions focuses exclusively on engineering and technology, offering specialized courses for high demand industry. Their courses are built by global experts and delivered by experienced engineers, ensuring practical job ready skills. ECT offers UK recognized qualification, whilst on the other hand, EIT provides Australian accredited qualification, many of which are recognized under the Global Engineering Accord. So both institutions also offer a range of professional certificate, which are short programs. Normally they range from three months in duration. So we also have a cutting edge tool facilitating live webinar and access to remote labs simulation. We also offer a personalized student support. Basically, then we have small classes and dedicated support to help students succeed. So once you're enrolled with us, you'll be allocated a learning support officer to be assisting you throughout the program. We also have a global learning community with students and members of faculty based across the globe. International networking and opportunity abroad are then enhanced. We also offer a high quality education. We offer a world-class education at an affordable price through innovation, delivery, and business mode. Today's topic will be from robotics to secure and autonomous navigation, the role of AI and smart sensors. Our presenter for the day will be Dr. Ali. He's also a lecturer and a unit coordinator at EIT. And these are some of his research areas: robotics, autonomy, sensor fusion, secure navigation. Dr. Ali, you can take control on your side.
Thank you so much. Thank you, Tony. Thank you for introducing me. Thank you, everyone, for attending to this webinar. So, as Tony said, we are talking about from robotics to secure autonomous navigation, the role of AI and smart sensors. So, let's go and start. What do we have today? We have an introduction to autonomy and AI, robotics, intelligence, and model. We talk about smart sensors and sensing modulation a little bit, AI and fusion, and optimization in AI and fusion. And then we have the most important part of each technology, which is safety and functional standard of that technology. Then I'll give you some address about practical computing platforms which are available in the market currently and are working in real time and real world. And then we go through some case studies for getting you some information about the topic that we talked about today, and you see how they work commercially, not only in lab and experimental. So let's start with the first topic, introducing autonomy and AI. Why did I call this autonomy, and why? What happened to the automation? So is there any...
Apologies, Dr. Al, did you take control of the slides, if I may ask?
Oh, sorry, what was that?
Did you take control of the slides?
Yes.
Oh, okay. So on my side, they're not moving.
Oh, okay, so it's not moving on your side?
Yeah, it's still at introduction. I'm not sure
really?
if, yes.
I changed the pages.
Dr. Ali, top left of your screen, please kindly take control of the slides. Right next to the record button, there is a take control feature, top left from your side, sir.
Now you can see difference.
Yes, we
Yes.
can definitely see a difference. Thank you so much.
Thank you. Yeah, sure. Thank you. And I'm sorry, everyone. I didn't take the control of the slides, so now you can see the slides better, I think. All right, so we start with the introduction to autonomy and AI. So let's talk about what is autonomy and why autonomy is accelerating. If we back to 5 to 7 years ago, there wasn't that much convergence of technology that currently. So previously, we couldn't run a full autonomous system on a platform. But currently, today, we can run everything fully automated. I will show you at the end of the webinar. So there are some real-world examples of that. And they are working with high performance. So what happened? There are 3 drivers for emergence or for acceleration of autonomy. The first one is the computing. What does it mean by computing? We have some hardware setup, such as Jetson hardware, such as Raspberry Pi, or even microcontrollers. They can work on edge. So what does it mean by edge? It means that they can make decisions, they can process data, and they can do whatever they need on a local area without requirement of connecting to any cloud for transferring data or for receiving data or for cleaning or filtering or some sort of stuff with data set. So they can process data in local area at point. So they can work on edge. Secondly, we have sensors. Previously, sensors, honestly, they've been dumb because what they've done was detecting raw data, a physical signal, say, for example, temperature, distance, or proximity, or speed, or acceleration, and then transfer these numbers, nonsense numbers, to the processor for further processing to the robots. And they had to do lots of process on them. For example, they had to clean these because we know that all physical signals around us are not clean. So they are highly noisy signals. They've been disturbed by other signals. right? Unwanted signals. So they have to be cleaned, they have to be denoised, the outliers must be detected and removed. And if there is any perturbation or some kind of stuff, makes our job way more difficult, right? So previously, sensors only detect these data, transfer these data to the robot, and the rest was the responsibility of the processors. But currently, we have smart sensors, so they can make decision. They can do some process locally in point at edge, so they can clean data some sort. They can compress data. They can find even they can find outliers and reject the outliers. So they can provide a more reliable data set and transfer these to the robot. Therefore, robots can trust on the sensors more than previous, not a little bit, but way more than previous, because the type of data that they receive is a clean, compressed, structured, and including lots of information. So it has tag numbers and calibration information and lots of other things. So this is the second driver, and the third driver is AI. So AI helps robots and sensors to make the best decision. How? By perception. So we have we had the models of AI previously, which was narrowed, and now they've been broadened. So previously, hundreds of features of engineering must work together for an AI platform to implement. But currently, today, we have um, AI which works based on training of multi-sensory data. So we have AI that can handle thousands or millions of tasks. So these three drivers get together and increase the speed of autonomy or increase the acceleration of autonomy in industry. So what we can see previously, we had industrial automation. So these industrial automation have been transferred to industrial autonomy. Because industrial automation, however, it was automation of the systems of industrial systems. For example, you have a PLC, which your PLC transfers some signals or commands to different devices, and they automatically do some tasks which have been predefined. But industrial autonomy means robots can make decisions. So robots based on AI can make decision, the best decision according to the situation. They can understand something beyond what the automatic system could understand previously. So when we are talking about AI, people who are working in academic or in purely in industry think of, all right, AI means machine learning, artificial neural network, and generally most of the people in current era, they think of chatbots. So while you are talking about AI, they think of chatbots. All right, you are talking about ChatGPT, you are talking about Copilot, you are talking about DeepSeek, and so, yep. So we have to say that we have multiple types of AI and chatbots. are categorized as one category of AI, which works based on LLMs, right? Large language models. We use large language models in our robots, but in robotics, AI is way more complex than chatbots. Why is more complex? Because imagine that you are sitting down the computer in front of your computer and typing something and ask something or ask ChatGPT to solve a mathematical problem for you. It solved the problem for you. And at best, the problem is solved perfectly. And if not, the problem solved with some wrong information. That's fine. Nothing would be happen. So you discuss with ChatGPT and the problem would be amended. But imagine that you have an autonomous vehicle driving in the street 60 kilometers per hour, 100 kilometers per hour in a crowded area. And there are pedestrians, pets, and the other cars. If AI, which is being embedded in that system, in that autonomous vehicle, makes decision by some incorrect approximation, what would be happen? Catastrophe. If a person, a kid, or a pet jumps to the street, what would be happen if AI cannot make decision, the best decision at the point? So that's the difference between AI that we are using in robots and AI that we are using in chatbots, such as LLMs. So we are using LLMs and other models of AI in combination in robots. Another thing is, while we are using AI in robots, our preferences using these AI in such a way that it can make its own decision on spot. It shouldn't be rely on the cloud. It must be able to make decision on edge, right? So that this is another difference between the AI which has been used in robots and AI which has been used in the language-based AI. So we have, therefore, we can say that AI is not an intelligence, but is embodied intelligence. So AI can understand the concept. It can understand not only the physical signal, but the object. For example, you have a robot, and this robot, say for example, an autonomous drone, it's working in a very noisy area, right? So it gets lots of signal, which are noisy signals from multiple sensors. So if AI was an intelligence, so it gets these signals only without understanding what does these signals mean? What does the object that signals come from mean? But AI is embodied intelligence. It means that it understands when you show that an apple, it understands what apple means, right? So we are talking about that later on a little bit further, but we have to know that there is a difference between embodied intelligence and intelligence. So embodied intelligence talks about objects rather than talking about only raw data, right? And why we say that AI is embodied intelligence, and it must be sort of, because while you have multiple data from sensors, these data if they only reflect the raw numbers, and AI only detects these raw numbers and process these raw numbers, it called as conventional type of intelligence. Whatever we used, for example, 6 years ago, 7 years ago, in robots mapping and object detection. But currently, while we are using AI in autonomous vehicle, driverless taxi in the street, they must be able to understand if a people is walking around in the pedestrian. Is it likely to cross the road all of a sudden or not? Exactly the same as what you're doing while you're driving. While you're driving, you predict the future behavior of lots of objects because you know the objects. You know the behavior of the objects. Therefore, we are going to end up with a model that we call it as a foundation model. What is a foundation model? Previously, while we wanted to program a robot, different types of robot, it doesn't matter if it was humanoid or if it was a drone, if it was a autonomous vehicle, ground vehicle, or whatever, we developed an algorithm, a certain algorithm, say, for example, algorithm A for robot B. And algorithm A was responsible for robot B to make sure that robot B do or does task 1, right? Then algorithm C developed for robot D, and it makes sure that robot D does task 2, right? But foundation model is beyond that model. So foundation model provides a generalized model. Provide a generalized model for the robots to make sure that robots get trained by a data set from a previous experience, from current experience, from prediction of the future, from behavior of the other robots. So that's what we call it as foundation model. So it trains across different robots, different tasks, and different environment instead of one model per robot, right? How those our systems would be possible, how development of those systems would be possible. That's because of the smart sensors, which are one of the most important part of the current technology in robotics. Smart sensors who are available for pre-processing, for processing, for filtration, for cleaning a data set, for removing the outliers, and transfer the signal, including lots of other information, such as a tag number for a signal, such as the calibration of a signal, right, of a sensor or a signal. So the smart sensors are some revolutionary technology in this era. It made it possible for the robots to be more intelligent, to be embodied intelligent, right? Without a smart sensor, it was impossible, right? Oh. So we talked about smart sensors in another webinar last year, so you can go through and get more detailed information about smart sensors and edge computing. So it is very useful for you as well. Now we are talking about the smart sensor, different types of smart sensors. We have different types of sensors. As I mentioned previously, sensors are very responsible for detecting some physical phenomena. For example, they detect pressure, they detect temperature, they detect proximity or whatever, or acceleration or velocity, without doing anything else. The only thing that has happened in the conventional sensors was at most amplification of the signal, because we didn't want attenuation on signal. But currently what we have is smart sensors. So these smart sensors, including, for example, in some autonomous vehicles or drone or robots, LiDAR, radar, and IMU, inertial measurement unit, or other types of these type of sensors. They all detect different data with different features, with different capabilities and strengths, and then process these data in some cases. So clean data and make it ready to transfer it to the processor of the robots. So they give the robot either autonomous robot or humanoid or drone or underwater mobile robots. They give a very accurate and precise geometry, structured geometry data set to the robot to be able to make decision for navigation, for path planning, for obstacle avoidance, for target finding, right? So they work all together. And if you look at an autonomous vehicle, for example, which is most obvious in these um, um, current, you can see that there are lots of sensors working together. Why? Why lots of sensors work together? Is it necessary all of these sensors work together? So can't we use only one sensor, one smart sensor, and get the accurate geometry? Let's see. Before I'm going to answer my previous question, I have to introduce you something which is very interesting. So this is the most interesting vision device has been developing. Actually, this is in R&D stage, in laboratory stage, which we call it as event camera. So event cameras are working differently because in conventional camera, what you have is taking a shot, a frame from whole scenario, so whole scene. This is the street, including lots of dynamic obstacles and static obstacles. You have trees, you have cars, you have pedestrians, you have birds, and so on. So while you take a photo using RGB cameras, it takes a frame from whole information available in that street. If there is enough light, if there is no dirt or contamination or pollution in the air, that's fine. You get a very high resolution image. But what if there is low light intensity? There is no sun. The story would be different. Yes, I know that we have different types of cameras or infrared or so on, but they are not as accurate as this camera is. It's called event camera, and event camera is the type of camera that does not work based on frame by frame imaging, but it works pixel by pixel. So every pixel, every single pixel in the event camera is an event. And the camera detects this event if and only if the light intensity would be changed. So if the light intensity would be changed, this event would be captured. How long does it take? Milliseconds. Milliseconds. In milliseconds, you get difference in each pixel. Pixels are working independently. Therefore, we have higher velocity in capturing information about the environment. And the most important part is light intensity doesn't impact the resolution of this camera. So the image your robot or your autonomous vehicle received by this camera is higher in case of the resolution, more accurate, and it gives a more accurate information about the um, geometrical information about the environment, right? So we call it as event camera, and it is the state of the art in the camera technology. Back to my previous question. I told you that we have multiple sensors work in one device. You have a robot, humanoid. So this robot wants to get information about the environment, right? In a factory or in production line or wherever you want to call it. So it must capture the information, um, geometrical information, such as distance or proximity or obstacles or so. Or you have a drone which is moving from one, for example, it moves from source one to destination two, right? So in between, there could be some field, some bushes, or there could be transmission line, which is the source of radio frequency interferences. So we have lots of noises and obstacles while the drone is moving, right? And imagine that while the drone is moving, just let me, yeah. And imagine that we have only our drone works with GNSS, right? In between the mountain, the hills, or in busy area, in crowded area, the signals possibly would be faded, and there is no signal received by the drone. Or imagine that this drone working only by using a LiDAR. If there is any transparent obstacle in front, because LiDAR, we know that LiDAR, LiDAR is a sensor which works with light and transfer the light as laser pulses, right? So while it's subjected to any transparent obstacle, we have the problem of reflection. So because it works based on time of flight, the light pulses transfer and reflected back, and time of flight would be calculated. For the transparent obstacles, they would be penetrated. So the drone would get confused in case of the obstacle and then bump the obstacle. So, and for the other sensors, for example, say radar, it gives you a very accurate geometrical information, but it has a low resolution in spatial geometry. Or for the camera, I told you what is the problem. The problem is light intensity. If there is a dark area, what would be happen? So what do we need? We need reliability. We need this information to be reliable for the robots to be able to trust on this information. We need, if one of these sensors failed, another one take over. If another one failed, two other or three others take over. And how is this possible? It would be possible by term that we call it as fusion, or we call it as sensor fusion. So we have sensor fusion, or in general, we have data fusion, which is a wider or broader concept of sensor fusion. Sensor fusion is very technical and is more hardware plus software based. So what does sensor fusion do? How does this work? Sensor fusion fuses different types of sensors in a robot. So you have autonomous vehicle, and your autonomous vehicle equipped with radar, LiDAR, camera, um, and sonar for parking assistant. And all of them would be fused, because any failure in an autonomous vehicle results in a catastrophe, right? So accident happen and people may die. So we don't need any error. We want the error to be minimized to zero, right? That's why we use sensor fusion, and in sensor fusion, we fuse all the sensors. How does this work? I will explain it a little bit later. So we have sensor fusion, and sensor fusion previously, actually in case of the conventional or classic sensor fusion, we have a term that we call it as actually the sensor fusion used a statistical the statistical method, statistical methods, to get this information and find the best estimation or out of the information it gets from all the sensors. So each sensor, data grabbed from the sensors would be treated independently. So it works with sonar, with LiDAR, with radar, with camera, and then gets all this information. If there is no data received by the camera because of the low light intensity or any failure, then it had other information from other sensors. Then it used some statistical method based on probabilistic models, such as Kalman filter or extended Kalman filter, or say, for example, Bayesian inference, and other type of probabilistic method to find the best estimation, right? That is how conventional sensor fusion works. But currently, we get AI combined with the classical method. Why? Because AI makes sure that data has been extracted properly. So while we are using AI, we use, for example, neural network to extract all data, all information. And then while this information extracted and structured, we feed all of them to classical method, such as Kalman filter, such as extended Kalman filter. Why do we need both of them? Because these mathematical methods are rigorous and they guarantees that this structure works robust, right? We cannot rely on AI independently. It must be combined with these conventional methods. For example, we have another thing that AI helps, or new generation of fusion technology helps, is the new generation of fusion technology is not working with each sensor independently. So it works with combination of the sensors as a unique system. For example, we have FAST, um, LIO2, which is a real platform, and it combines IMU and LiDAR information both together, act treat with both these information as a one set of information, right? So there is no the latency between analyzing or processing these data. Or we have R3 um, Live plus plus, which went beyond that. So it works with IMU, IMU radar, LiDAR, and combine all these information and RGB cameras, and treat all of these information as a one single data set. So it increases the reliability and let the autonomous vehicle, let the robot, to trust to these devices. So we have AI and fusion, as I explained. So this is the combination, and we have um, plan for optimization for the AI. In AI structure, in autonomy, a structure of the autonomy, we have perception, we have localization, we have planning, and we have motion control. What does each of them means? Perception means, imagine that there is a robot and robot is in the environment. Perception means robot detects the environment, see what is around, what the robot has been surrounded by. So it detects the environment, understand the environment. So it's called as perception. We have localization. Localization means the robot asks itself, where I am currently, what is my coordination in this environment? Am I in the origin or am far from the origin, and how origin would be defined? Then planning. Robot asks itself, what is the next step? Where do I go in the future, in the near future? And motion control means, how should I go to reach to the next destination? So is there any obstacle that I have to avoid? Is there any hazard? Is there any special path that I have to meet by follow this path? So this is motion control. But all of them has been improved, has been optimized using AI. So perception has been improved because in using AI, And in the new generation of the robots, robot can understand if a person, if a human is standing here or a human is crossing the road. So it can understand the difference between these two concepts. However, previously we used some sensors such as cameras or LiDAR to detect the edges, detect the object, the geometry of that, and create a 3D map of the scenario. But if the object moved, the robot cannot understand, couldn't understand what does it mean. Or if there was a human inside by the street, the robot couldn't predict, because this is a human, it may propose some unpredictable behavior, jump to the street or run to the street or do something funny, right? But AI helps the robot understand these kind of matter, help the robot to understand the objects, semantic, right? For localization, for planning, also AI can help by combining conventional methods such as model predictive control, which is using in conventional method, or other mathematical based algorithms which are highly rigorous and they are working robustly, but AI gives them some sort of soul, right? Then we have standards which are very important for any technology. We need this standard, especially for this type of technology, which could cause lots of hazard and issues. For example, we have autonomous robots that must work based on ISO 26262 for safety purposes. We have SOTIF, which is ISO 21448, and it's been developed by at 2022. This is it called as SOTIF, called as unknown unknowns. And this is very important standard for the robotics, for AI and robotics, right? So if there is a robot that do not comply with these standards, definitely it cannot come out from the laboratory. So practical computing is Jetson. And as an example, Jetson is a hardware setup which can run autonomous action fully. It's been used in different devices and equipment in different autonomous vehicles. We have Raspberry Pi in smaller scale, like for teaching purposes, for laboratory purposes, for fun and hobby. By the way, they are working perfectly for autonomous vehicles. As you can see, whatever I've already talked about that is not only a story, is really commercialized. So you can see Waymo is driverless taxi, a company that provides driverless taxis. So Waymo is running all over the United States, in Phoenix, in San Francisco, in Arizona. So everywhere that you go, you can see the driverless taxis running without, I don't say without, but with minimum error, right? With minimum issues. And all of these devices use whatever I've told you here, introduce you here, such as smart sensors, such as fusion, such as AI, and so on. Another example is BVLOS, has been driven by Zipline. Zipline is a company for delivering the critical medication. So it works in Africa and United States both. So we have critical object has been moved by these drone, fully automated, and we have warehouse autonomy, which has been improved earlier than the other two examples. For example, Amazon fully automated, no labors, and they are all based on robots. We have, if we want to conclude whatever we talked about today, We talked about AI and combination of AI and smart sensors and how they improve the performance of the robotics and changed, or they are working as a revolution in robotics and robot industry in current era, right? So we talked about embedded systems and embodied intelligence and foundation models and sensor fusion and future of the robotics. So at the end, we have actually I'm running actually I'm serving as an editor of these journals. So this is a special issue of the journal Electronics, MDPI, called as AI-driven intelligent and secure navigation in next-gen autonomous systems. If you have any paper and you are willing to publish the paper, so it's been peer-reviewed in this journal, you can scan this barcode and get the information how to submit your manuscript. That's the end of this webinar. I hope you enjoyed the webinar, and thank you so much for being patient and being with me for that long. Thank you so much.
Thank you very much, Dr. Ali. The session was very educational and very informative. I hope our attendees also felt the same and they took something with them from this session.
I hope so.
Moving right along. So what today's topic basically covers, it covers the following: School of Engineering, Electrical Engineering, Mechanical Engineering, Industrial Automation, Instrumentation, Process Control, and Electronics. All of these are offered by EIT and ECT. You can check that on our website. You will be assisted. Let's just move right along. So on your screen now, these are our upcoming programs. Engineering Institute of Technology, EIT, and Engineering College of Technology, respectively. On the right-hand side, you'll see the start date. Mostly they're starting next year. There's January, and there's Feb also. So you can also visit our website for more information on this particular fields that we offer. So on your screen now, this is certificate of attendance, the QR code. You can scan the QR code, but I'm going to be sharing the link just now on the chat. Please, so you just need to click on the link, then get your certificate of attendance. Just make sure that you use your real name when your real name basically, then when you are claiming your certificate. So let me just share that now with you guys on the chat platform. I think we have a couple of questions. Let me quickly check. Yes, this is the Q&A session. So I've seen few questions. I'm not sure if you're able to see them, Dr. Ali, or should I read them out to you? Check. Okay, I think we have one question from Mark. Mark is saying, kindly elaborate on drive-by-wire in slide 19. I think we already passed that. But yeah, Mark is just saying that, can you elaborate on drive-by-wire?
So can you go back to the, can you go back to the slide? Yes,
go back
please.
to slide 19. This is slide 19.
So this is slide 19. Do you mean this
19.
slide or?
Yes. Yes, he's saying that, can you kindly elaborate on drive-by-wire in slide 19 for us? So I'm assuming this is slide 19. They just want elaboration on this.
Yeah. So, okay. So what do we have normally in fusion and AI related, actually fusion related, while we have AI combined with fusion, and in robotics, in general, we have perception, and perception means while we have some intelligent device, first of all, this device must detect the environment. So for this purpose, we use different types of sensors, all collaborating together in a robot, like a humanoid, for example. We have camera and we have LiDAR and, for example, sonar, right? So they are fusion and they are working and they detect the environment. Say, for example, a robot is located at a bushy environment. So there are lots of trees, right? So it must understand, it must capture these objects using different types of sensors, fusion all of them, gets a proper, accurate image of the whole area. Is exactly like a human while you are going to an environment which is unknown for you. What do? You have to do perception first. You have to look at the environment, surrounding environment, and understand what is what, right? So it happens to the robot as well. And then localization. So what you have to do is you have to localize. Where am I now? So what is my coordinates? So where is the origin? And how far I am from the origin, right? Why this is important? Because you have to map your movement. You have to be able to move to reach the target. If there is any eavesdropper, you have to be able to control your path, to plan your path, to be able to avoid this eavesdropper, to protect the information that you transmit or receive from the source, right? So this is a general idea about this architecture, but to go deep down, I'm afraid it's not that much time. By the way, if there is any opportunity, you can send me an email later on, and then we can discuss it later.
Okay, thank you very much, Dr. Ali. Hopefully it does answer the question that you had, or the clarity that you were seeking in that regard. So yeah, you can just quickly, guys, I've already shared the certificate of attendance link. You can click on that, claim a certificate, or scan the QR code on the screen now. So yes, the PDF for this session will be shared to your emails if you have registered for this webinar. So it will be shared within two business working days. So just check your junk folder, spam folder, if it does not appear in your inbox. I think we are on time. Let me just check if I can get one more question. Let me just quickly check if there's any. There's a question from our side. Doctor, do you think it is possible to merge sensors to have a singular sensors rather having multiple sensors to assist robotics?
Yeah, definitely. Actually, it is possible. If you see the conventional type of robots, actually, I've worked some in the laboratory as well. So we used only single robot for navigation, but it's limited to the laboratory environment, or if you want to just prove certain algorithm that it works, so you get this information. In commercial environment, definitely we must use fusion, and the reason is if that sensor fails, you must have some alternative, right? But in laboratory scale, in a small scale, if the purpose of using the robot is not the sensor itself, but some other extra method. For example, you are developing a path planning algorithm, or you are developing an obstacle avoidance algorithm, or target pointing, or something like that. So your purpose is different. Then you can use only one sensor and run the mobile robot according to that single sensor. But the answer in general is yes, definitely you can use one.
I hope it answers the attendee's question. Thank you very much, Dr. Ali. And yeah, once more, thank you for the very informative session. So I've learned a lot also as a host of this session. And it's very, very intriguing, very interesting. And all the attendees, I hope they did the same. So we are at the end of our session. So on the screen, these are our contact details, EIT and ECT respectively, or you can visit our website. Our course advisor will be in contact with you, offer you information that you need on our programs or EIT as a whole. Any last words from you, Dr. Ali?
Nothing, just I want to say thank you to you for organizing and managing everything. Thank you so much. I appreciate that. And Seshifo, for helping us. Thank you so much. I appreciate that. Thank you everyone for attending and bearing with us in this webinar. Appreciate that. Thank you.
Thank you. We are closing the session, and I'll just be answering your questions on the chat box. I think they're related to EIT or the course offerings. Yeah, thanks once more time, and you have a great day, Dr. Ali, and everyone else also.
Thank you so much. I appreciate that, and see you next time. Bye.
Bye-bye.